Yesterday we talked about finding the slope of the tangent using the chart, where we looked at the graph and we evaluated a whole bunch of points as we got closer to our desired point. This video is going to show an algebraic method to find the slope of the tangent. And so what we're going to do today is we're going to calculate the limit as x approaches a of f at x take away f at a over x minus a. So this is like our fancy slope formula. And this part, the limit as x approaches a, that is like the table that we did where we calculated a whole bunch of slopes. The limit allows us to calculate all those slopes in one section. So let's take a look here. So we're going to find the slope of our tangent for this function, f at x equals x squared plus 1 at the point P, 1, 2. So our x value here is our a value, so a equals 1, which means that we're going to find the limit as x approaches 1 of f at x minus f at a all over x take away a. So our next line is we're going to substitute in our known values here. So we are looking at what happens as we get close to 1. Our f at x, we know, that's x squared plus 1. F at a is just our function, x squared plus 1, evaluated at x equals a. So we're going to have a squared plus 1 here. Or sorry, our a is 1. So 1 squared plus 1. And then we've got x minus 1 on the bottom. So now we're going to simplify as much as we can. So on the top, I'm going to have x squared. Let's see, I've got 1 minus 1 minus 1 again. So I'm going to be left with x squared minus 1 on the top and x minus 1 on the bottom. Now, if I substitute in my 1 right now, the value that I'm interested in, I'm going to get 0 on the top and 0 on the bottom. So that doesn't tell me anything. That's called an indeterminate limit. So we need to simplify a little bit further to see if we can get an expression that is not indeterminate. So, yes, it is important to continue writing the limit until you've evaluated it. Let's factor the top and factor the bottom, okay, or rewrite the bottom. Now what I notice is that I can cancel out x minus 1. I should note that x can't equal 1, which I already kind of know because my limit, I'm not really going to equal that value. And now what I can do here, even though x doesn't really equal 1, now I've got a situation where I can substitute in my a value and I can get an answer for my solution, for my slope of the tangent. So subbing in here, 1 plus 1 gives me the slope of my tangent is 2, which is actually the same problem we did in the table. So we know that that is true. Let's take a look at another example. Here we've got the curve f at x equals 4x minus x squared, and then we're looking for the slope of the tangent at x equals 2. So our a value is 2. So I'm going to find the slope of my tangent is the limit as x approaches my a value, which is 2, of f at x minus f at 2 all over x minus 2. So this matches my slope formula from the first page that had a's in it. F at a over x minus a. I can't forget my limit. X goes to a. Here I'm just substituting in the value that I know. So I know that 2 is a, so I've put that in wherever I see an a. My next step is going to be to substitute in and evaluate. So f at x, I can just write that down. And then I'm going to take away f at 2. So I've got 4 times 2 minus 2 squared all over x minus 2. So I can keep going. Let's see. 4x minus x squared minus 8 plus 4. All I'm doing here is I'm expanding and simplifying. I've got minus x squared plus 4x minus 4 all over x minus 2. So that I can factor that expression, I am going to take out the minus sign. Trick that we've used in other situations. And then I'm going to factor the top. So I haven't evaluated my limit, so I need to keep writing it down. I can actually factor this as a perfect square trinomial, which is x minus 2 all squared. If you don't see the perfect square trinomial, that's okay. You're still looking for two numbers that add to 4 and multiply to negative 4. Or sorry, multiply to positive 4 and add to negative 4. Always multiplying to that last term and adding to the middle term. So here, now I notice if I substitute in 2, I get 0 on the top and 0 on the bottom. So that's an indeterminate limit. I can't say that my answer is 0. So I have to do a little bit more. So I notice that I have x minus 2 squared on the top and x minus 2 on the bottom. So I can cancel out one of those, and I'm left with minus x minus 2. Now I can substitute in my a value and evaluate my limit, and I can say that the slope of my tangent is 0. This is not indeterminate here because I no longer have that denominator. Should add that x can actually equal 2 here, just to make sure that we're not dividing by 0. So that's another example of finding the slope of the tangent. For our third example, we're going to use our same formula. So the slope of our tangent is going to be the limit as x approaches a. In this case, it's minus 4. And I've got f at x, just my function. Take away my function evaluated at a, which in this case is minus 4, over x minus 4. So my a value is minus 4. And the formula that I'm using is just from our first slide, which is our limit as x goes to a of f at x minus f at a over x minus a. I'll change that 4 to an a just so our notation all matches. So let's substitute in what we know, and we'll do some simplification here before we evaluate our limit. So f at x is 2x over x plus 1, and we're going to take away f at minus 4. So 2 times minus 4 over minus 4 plus 1 all over x minus 4. Now I've got some work to do in the top, in the numerator. So 2x over x plus 1. See, I'm still going to be subtracting, I think, here. And I've got 8 over 3. Let's see, because I'd have negative 8, negative 3, and then I still have a negative. Okay, over x minus 4. So now I need a common denominator to add the two fractions on the top together. I'm going to get that just by multiplying them together. So I've got 3 and x plus 1. So that means that my first fraction, I need to multiply by 3. So I've got 2x times 3 over x plus 1. And then I'm going to multiply my right-hand fraction by x plus 1, so that my denominators are now going to be the same. Okay. Oh, and going back here, I am taking away negative 4, which is the same as adding 4 there. Okay, So let's keep going. We've got the limit as x approaches -4. That's 6x, take away 8x plus 1, all over 3 times x plus 1, all over x plus 4. I can simplify and collect like terms in my numerator. Got 6x minus 8x minus 8, all over 3 times x plus 1, all over x plus 4. And I can keep going. I've got minus 2x minus 8 over 3 times x plus 1 over x plus 4. Maybe you can see where this is going. I'm going to rewrite I'm going to do 2 steps in one here. I'm going to rewrite my triple-decker fraction into a division question, and I'm going to factor my numerator. So I'm going to take out a minus 2, which is going to leave me with minus 2 times x plus 4 over 3 times x plus 1. And I'm dividing by x plus 4. Okay. Now we know that when I'm dividing fractions, that is really the same as multiplication. So I'm going to change the division to multiplication, and I'm going to flip my fraction. So I've got 1 on top and x plus 4 on the bottom. That's going to allow me to cancel out the x plus 4s. Say that x can't equal -4. We know that. That's where we're evaluating the limit. And now we're at a point where we can substitute in and evaluate our limit. So we've got minus 2 over 3 times x plus 1. And that means that the slope of our tangent, if we plug in minus 4 there, we're going to get minus 4 plus 1, which is minus 3. And we get 3 times 3, which is 9. And so we get the slope of our tangent is going to be 2 over 9 when we evaluate at that point. And those are some examples of how to find the slope of the tangent to the curve at a particular point using limits, which is our algebraic method.